Hello, everyone. My name is Alex Spiridonov, and I'm a product manager for Google Cloud AI Accelerators. And I'm here today with my colleague, Alan Wong, to tell you more about developing Ray applications with Google Cloud TPUs. At Google Cloud, we are proud to be the only cloud provider that offers the full range of AI accelerator choices, from NVIDIA-powered GPU offerings to our own custom-built Tensor Processing Units, or TPUs. Now, Google Cloud TPUs represent nearly a decade of innovation in AI supercomputing. We started in 2015 with TPU v1, our inference-only accelerator. In 2018, we launched Cloud TPU v2 pods, where for the first time, we connected 256 TPUs with an ultra-fast interconnect to enable training at scale. 2 years later, we quadrupled the number of chips to 1,024 and introduced liquid cooling for even more performance. And 2 years later, we quadrupled the number of TPUs again to 4,096 and introduced an ultra-fast optical interconnect. So this brings us to today. Just 2 weeks ago, at Google Cloud Next, we introduced the Cloud TPU v5e, our newest and greatest AI supercomputer. Now, what makes Cloud TPU v5e so great? Well, in his brilliant keynote this morning, Robert talked about the importance of cost efficiency and scale. And that is exactly what the Cloud TPU v5e was designed to do. v5e is incredibly cost efficient. It offers up to 2 times more performance per dollar for training and up to 2.5 times more performance per dollar for inference compared to Cloud TPU v4. v5e is also incredibly versatile. We support the most popular ML frameworks, including PyTorch, JAX, and TensorFlow. And, of course, we integrate closely with Ray. Finally, a superpower of Cloud TPU v5e is its amazing scalability. With v5e, you can train large language models and generative AI models using tens of thousands of TPU chips with our new technology, which we call multi-slice training. And after training or fine-tuning, you can run inference on the same TPU v5e hardware with great cost efficiency. And you can serve models with up to 2 trillion parameters using a technology which we call multi-host inference. Now, all of those capabilities come from the magic of combined hardware and software optimizations. On the hardware side, they're powered with our ultra-fast inter-chip interconnect and with our highly efficient Google Cloud Data Center networking. And on the software side, we constantly optimize the software stack, including XLA, our AI compiler, to get the highest performance and efficiency for both training and inference. Now let's take a closer look at our performance numbers. As I mentioned, TPU v5e is highly cost efficient, offering up to 2 times greater performance per dollar for training large language models and generative AI models. And you can achieve even greater performance per dollar if you do your training in int8 precision, which is natively supported by the v5e hardware and the software stack. Now, Robert talked this morning about the importance of scaling to meet the growing demand for AI compute. And this is where Cloud TPU v5e really shines. You can seamlessly scale training your models from 256 chips all the way to more than 32,000 TPU chips. 32,000 TPU chips to train a single model. That is 128 full TPU v5e pods. That's an incredible amount of compute. And with multi-slice training, you can achieve nearly perfect linear scaling for your training job. That is a game changer for training your large language models and generative AI models, because now you can train even larger models in less time simply by adding more TPUs. Now, of course, after you have trained or fine-tuned your model, you need to run inference on it very cost efficiently. This is another area where Cloud TPU v5e achieves great cost efficiency and great performance per dollar, with up to 2.5 times greater performance per dollar on leading large language models such as Llama 2 and generative AI models such as Stable Diffusion. And of course, as AI developers, we care both about throughput and latency because we want our AI applications to be very responsive for our users. And so in latency, v5e achieves up to 1.7 times the speedup compared to Cloud TPU v4. Now, of course, we know that as developers, you want to use TPUs in your preferred way to fit your development lifecycle. And this is where Ray on Cloud TPUs really shines, because Ray makes it seamless to train and serve LLMs and generative AI models using the latest and greatest Cloud TPUs. For training, you can start by developing a model locally on your laptop, and then you can seamlessly scale it up to hundreds or even thousands and tens of thousands of TPUs using the same familiar Ray APIs that you know and love. You don't need to be an expert or have a PhD in distributed computing. The magic of Ray is that it manages all of the complexity of orchestrating this massive amount of compute. With just a few lines of code, you can take advantage of Ray auto-scaling, auto-provisioning, and fault tolerance, just as you do today. Needless to say, Ray is also great at fine-tuning pre-trained models, using your data and your tasks to solve your users' needs. And finally, after you have trained or fine-tuned your model, you can very efficiently use RayServe to have your model running on a TPU within seconds for inference. And when you're ready to deploy that model in production, you can use Ray to harness hundreds of TPU accelerators to meet the most demanding needs of your users in production. At Google Cloud, we love Ray because it really makes developing on TPUs for training and inference super easy. But don't just take my word for it. We are here to show you some amazing demos that show you just how easy it is to get started with Ray on Cloud TPUs. And to show you more, please welcome to the stage my colleague, Alan Wong.
Thank you, Alex. Hi, everyone. My name is Alan Wong. I'm a software engineer at Google. And today, I'm excited to show you how you can easily take advantage of all of these exciting advancements by demonstrating to you how easy it is to train and serve Llama 2 using Ray with Cloud TPUs. So I'm going to go ahead and show you this notebook here. And essentially, I have some starter code just to get us started. So I've already used the Ray cluster launcher to spin up a Ray cluster with TPUs attached to it. So all I'm going to first do is connect to it. And what you can see here is a snippet of code that essentially wraps Hugging Face. And what I'm trying to say here is that I want to use a Llama 2 model, 2 billion parameter variant. And generally here, I'm just going to initialize and then run some training. If you were to use something like Ray data for all of your pre-processing, it's a great opportunity for you to insert that here. But regardless, this could be pretty much any standard workflow. Right now, I'm using Llama 2B. What I'm going to show you first is actually how can you run this on a Ray cluster with TPUs. So step one of that is actually, let's just connect to Ray. I know a lot of you are familiar with Ray. This is pretty simple. All I'm going to do is mark ray.remote. So if I were to execute this, for instance, init and run hf.remote, then this will execute on my Ray cluster. But I don't want this to run on any resources. Specifically, I want this to run on a Ray worker node that has TPUs attached to it. So I can easily mark a resource, TPU 4. And now if I were to invoke this function, this will run on the Ray cluster with a Ray worker with 4 TPUs attached, because TPUs are a native resource in Ray as of 2.7. But that's not all. I also want to make sure that the function that's executing can also take advantage of the underlying hardware. And we do that through the ML framework. So what I'm going to do next is I'm going to actually import Torch, which is what Hugging Face is using under the hood. And I'm going to import Torch XLA. And now whenever I execute this, then Hugging Face will actually take advantage of the underlying hardware. So we should be good to go. Let's go ahead and execute it. So what you can see pretty quickly is that we were able to import PyTorch XLA, load a 2 billion parameter variant, and we are using libTPU, and these are really key indicators that we are training on TPUs. So just like that, I showed you how you can easily take a 2 billion parameter model and run it on a Ray cluster from your notebook. But honestly, this is a 2 billion parameter model. I actually want my next model to be bigger. I want it to use hundreds, if not thousands, of TPUs. So what I'm actually going to show you next is how easy it is to take code like this and then scale it up to a TPU cluster with much more compute than this. So I actually already have this main file here. It's pretty much the exact same code that you just saw before with a bit more logging. And what I'm saying now is I want to use a 70 billion parameter variant, as well as a few other arguments. So main challenge here is that I actually want to run this remote function on all of my Ray worker nodes that have TPUs attached to it. So fortunately, it's very simple through Ray. So one thing I know is that Ray already knows about the number of TPUs that are within its cluster. Each TPU has 4 chips, so I can easily calculate the number of hosts automatically through Ray. And now what I want to do is take this remote function and run this on every single worker node. So I can just do a simple list comprehension like this. And this returns a list of handles, so let's just go ahead and get the responses from that. So just like that, this will actually take advantage of all the compute in my Ray cluster with hundreds of TPU chips. This will actually take some time for me to kick this off and load, but pretty much what I would say is something like, Ray job run Python main. I've already kicked this off ahead of time. Let me quickly just show you. So you can see this job dashboard. You can see the same logs imported PyTorch 6a using libTPU. And if I were to scroll down, pretty easily you're able to see that this is running on TPUs. And just like that, I showed you how you can take the code that you were running in a notebook to train on a production level cluster with hundreds of TPU chips. And this is all thanks to Ray's simplicity and its orchestration capabilities under the hood. So I'd actually love to just wait here with you and watch this pre-train for several weeks. But we have an exciting Ray Summit ahead of us, so let's just fast forward to whenever the model has actually been trained. So serving large models is actually pretty unique. You typically need a large amount of compute to even run these things, especially if you have a latency concern, which you probably do. If you are looking for an accelerator option that is both performant and price efficient, TPU v5e is a great option for this. But like I mentioned, serving large language models is pretty unique. So the question is, how do I even do it? It's not so simple. Or is it? Let me go ahead and show you. So I have a bit of starter code here. And essentially, as an ML developer, the gist is I have done all my pre-training in Python. And generally, what I would like to do is actually just write an abstraction like this. I want to write a model server that can load a checkpoint. Once the checkpoint has been loaded, I should be able to send any batch to it whenever I want to. And generally, I wrote this in Python. I don't want to have to cross a programming language barrier, switch stacks, or anything like that just to serve something like that. Luckily, RayServe makes this really easy for us to do. All I have to do is import RayServe, and then mark this as a deployment. And again, I actually want to make sure that this runs on the TPU hardware under the hood. So I'm going to say Ray actor options and take advantage of the TPU. And it's actually just as easy as that. This is a deployment that would work. But honestly, Ray has some other great things. It already has native integration with Gradio. So if I were to just copy and paste this code into my deployment, then I can easily just say something like serve run, and then Gradio. But again, this can take some time to set up. So let's just fast forward. I already have this set up here as a Gradio server. And let's actually just send it a prompt. This is a text completion prompt. Let's just ask it a very easy question. So I believe the meaning of life is to be happy. What a great answer. And just like that, I showed you how you're able to easily take your pre-trained model using Ray on TPUs to serve it using the exact same stack that you used to pre-train it. And overall, in conclusion, what I've shown you today is that you're able to start with any arbitrary code, PyTorch or JAX, test training on a single TPU, easily scale it out to hundreds, if not thousands of TPU chips, serve it on a single TPU, and then scale your model in production, all with TPUs. There's a lot of other features in Ray that I didn't get a chance to show you today, but we get these all for free because Ray is heterogeneous. It's hardware and software agnostic. And overall, I think we are at a point where we can use, we have a software stack that allows us to have performant, modern, and robust stacks, all powered with Ray on TPUs. Thank you for your time.